Hi friends, welcome you all to the session 30th of form-based development. In this lecture, we are going to be looking at the ARM programming tools. Okay, so we have covered mostly on the hardware side so far. Memory, processor architecture, coprocessor, all those features, modules which are inside the processor. Now we are going to spend some time on programming tools that are running on the development platform. It could be a PC running in Windows or running a Linux OS. So we have some tools running on the development platform. When I say development platform, it's not the ARM based hardware platform, that is the target platform. Development platform is where we develop the software that needs to run on the processor. So these programming tools are running on the development platform. So we will spend some time on understanding them and how to interface them with the assembly and C programming software. So the focus of this discussion is going to be on just a brief overview, okay, a very top level overview of various tools available, and based on the processor that we choose, the tool that we need to use will also be defined. So to the tool chain. So this discussion is only to give you a flavor of what are the tools available, and I urge people to go into those tools specifically based on the processor that is being used, especially if an SoC, suppose you are buying an ARM based solution from the third party, there may be so many companies making the chip using the ARM core. So they may have their own tool and the OS integrated already. So based on the development platform, the tools may differ. So the idea here is to give you an overview of what are the tools available, so that any tool that you look at, you will be familiar with the overall functioning of them and what they do, so that once you read the manual of those specific tools, you will understand them better. So after talking a brief, talking about some tools on ARM-based development platform, that is what is being supplied by ARM as a development platform. There are some standards defined by ARM for how to interface a C program or a C++ program for that matter with the assembly of ARM, okay, to generate an executable. Okay, so an executable could be built only with a C source file or C and assembly, and then of course some libraries coming along with the ARM tool. This could be supplied by ARM or a third party tool vendor or the SoC vendor. So it could come from any various sources, but they all comprise some standard which ARM has defined. That's called ARM procedure call standard for a particular programming language to be interfaced with the assembly of ARM, and then how it uses the registers in the processor. So we will study them a little bit more in detail, and then we look at a sample implementation, okay, using mental graphics tool. So this is going to be our focus today in this lecture. Okay, let us first understand what are the various names or synonyms or acronyms or whatever you call are related to the tools. Okay, this is what you hear more often about tool chain. So let me define what it is. In software, okay, now we are all talking about software, okay. So as I mentioned, I will be showing you a picture about how the target platform is going to do a development platform. Here, let us see what is the tool chain is. In software, a tool chain is a set of programming tools that are used to create a product. A product could be an executable. Okay, it's not something you can see or touch, but this is an executable coming out. Okay, a software which will be downloaded into the target hardware and run. The tools may be used in a chain. That means one after the other. This tool is used first, and then its output is fed to another tool. Then that output will go out to another tool. Then finally, what you get is an executable, which can be downloaded onto the target platform to run that and see how it behaves. Okay. So the tool chain is used basically to develop this software. Toolchain is used widely to refer to any set of linked or interrelated developments. So they are all interrelated because they understand one format. So this tool generates an output, and the next tool in the chain should know what's the format of this particular thing and how to interpret it. Then only it will be able to use this input to generate an output. So they are all interrelated. It's not that you can connect to tools which do not understand each other. A simple software development toolchain consists of a compiler, linker, loader to transform a set of high-level language source code files into an executable program or a library. So you can have multiple C files, okay, and then compile them, generate multiple OBJ files. This is object file, okay. Then we may have ASM files also. That will be assembled by an assembler. This is a compiler, right? And then this is an assembler. So assembler and generates an output file. Okay, it would be dot yes. And then what you do? All these OBJ files and files coming out of this assembler, you can use a linker to link them all. Okay, to generate a linker file. Linker format also .sql, so many things are there. And now we can actually generate an executable. When you say executable, then we know that the code or data, all those things are placed somewhere in a memory. Okay, we know where it exactly goes. So there may be a separate tool for loader could be used, or we could use the linker. We could add a separate another scatter file for that. Okay, I will explain that in the next session. Scatter file is actually decides where this particular code or data segments reside in the memory, going to reside in the memory. Okay, so this will be the executable. Now, sometimes you may not be interested in generating an executable, but you are interested in getting a library. That means it may not be a final program executable, but it's a part of the program. Maybe it gives all the floating point operations captured there. So if anyone wants to use this library, they can integrate, link it with their own code and generate an executable. So linker library is not an individual executable because it needs to be connected to another set of process, code to generate an executable. But it's an intermediate executable, I would say. So we could do any of these things based on what is an input to a particular tool and what you want to do it. Okay, so there are different possibilities. Let us I will explain you some of the things. So it also provides interfaces to the operating system. What I mean by operating system interface means the final executable may have an image of the OS also integrated with that. Okay, or maybe OS is running already, and then if it is a Linux or something, maybe you can download only your application and copy it into your hard disk and then run it as a separate application. So that is a different. It depends on whether it's an embedded world or it is in a PC world where you have a OS already running there, and then you generate an executable and run it on them. So we might, in case of normally in the embedded scenario, the OS is also integrated with the application, and then a single executable or an image is loaded into the hardware. So OS is already there in it, along with your own application code. So when the processor reset happens and then it comes up, OS comes first, and then gives the control to the application that you have made, and then it runs on the hardware. So there must be some way of connecting these two. Okay, OS calling the application or application calling some routines of the OS. So that kind of interfaces are also provided by the tool. What is a debugger? I will explain you. Just hold on. A complex project such as a video game needs tools for an example. This is a software tool that I have been explaining. Now, a typical video game, if you want to do, then there are tools to create sound effects, music, or three-dimensional models, or animations, and further tools for combining these resources into finished product. So, this is also a tool chain as far as the video game development is concerned. Okay, so tool chain is not specific to only the compiler and the tool or user. It could be a tool chain for developing a video game where you will have different kinds of tools to be connected together to generate an output product. So in a typical compiler linker, output product could be a library or it could be an executable. Okay. Now let us talk about ARM-based development environment. So this is a typical environment I was talking about. So this is the development platform. Okay, let us have a clarity on that. Okay, this is a development platform and this is a target platform. Okay, so what I mean by that is this is the chip. What you can see is a ARM processor. Okay, now this is connected to the development platform to a JTAG port. Okay, this is an interface. I will talk about this a little bit more in the next session. So you may wonder what is the need for this JTAG, right? The reason being the executable or the building the library, those things are done in this platform. And once that is done, it needs to be finally put into the target hardware before giving the power and then maybe giving a reset button here somewhere and then restarting that, starting that particular application. So and then not only that, not only loading the software through this cable, we also debug it. What I mean by debugger is the debugger is what is running here. We have front end tool which will have all the necessary features to look at the program control. Okay, you can stop the particular program execution and then look at all the register content. Whatever the tool that we have seen in the simulator, it doesn't have an hardware interface, but we can have a hardware interface and then run the software and then get the output from the hardware, and then we will be able to look at all the register content, variable, whatever variables we are modifying at a different point in time during the execution. So the debugger helps us in providing that kind of a interface so that we will be able to see what is being done by our software, whether is there any mistakes or is there any bugs in the code, is it behaving the way it is expected to. So those kind of things can be done before the application is tested fully, debugged fully, and then it can be released to the final product. So this target platform need not be the final platform. So it could be a development platform. We might have this chip only in the final, maybe your product goes into a car or it could go into a missile. So they may have the same processor, ARM processor what you are using here, but it may not have all these interfaces to debugger and connecting and then checking it. So before we put our code into this target final product, what is being done is we use the similar processor in the development as a development platform and then test the software. Then run lot of test cases, not few test cases, a set of test cases to make sure that different scenarios you generate different inputs and interrupts or timing scenarios and verify that the software is taking meeting all the requirements and it is very stable and reliable in the development platform, and then take it to the final in the target platform. Okay, in this target platform, I would say that it is also closer to the target, the actual target, but it is used as a development for the development. So maybe we can call them as the target hardware and then the development platform. This whole thing could be considered as a development platform because we are using this also is not a final target hardware that we are using. It could no, it is a intermediate stage where it has got all the provisions to be connected to the PC, and then we will be able to see what is happening there. Okay, and then finally it will be put into the final product where you will be able to see that it works as according to the specification. So this is what normally done in any development stage. So what are the tools are used in the PC? Okay, uh, this is a typical scenario where I have shown this in the beginning of the lecture. So C source files, they you can even consider it as a C++ or any other file, any other source also. But accordingly the tools will change. Okay, once the source file changes. So there are C header files, and then what it generates is an object code. And maybe we can have an assembler also, which is taking in assembly files. So you may wonder which are the things will be in C source and which are will be in assembly. Normally, the time critical modules will be implemented in assembly, and then most of the functionalities will be implemented in a higher level language. So what is the need for going in for assembly? Because some of the things which you want to have a closer control on how much time it takes, how it executes, those things if you want to time critical routines if you want to write it, then it is better to go in for a assembly file because you will be able to optimize it, making use of all the features of the processor and create an executable which is in terms of code size as well as in terms of performance is better. I'm not saying that the compilers will not generate very optimal code. There are so many optimization flags and there are very good technologies in the compiler generation that they also develop they also generate output files which are closer to our assembly file whatever you do, but still you understand your application scenario much better than what the compiler could do, and how can you communicate that to the compiler. So there may be some limitation on what you can do with the C source file or C++ whatever high level languages. So we can develop critical routines in assembly and then use standard features of libraries. Okay, I will tell you some examples of where we use libraries. Simple example is printf. We don't want to implement printf because it is all already standardized and it is available as a library. So there is no point in spending time in writing a printf routine. So similar to that, there are so many library files which are already implemented and they are very optimal implementation of that is available for a particular target platform. So we can use those library files and link it. Here only what you do is we provide a scatter file to give a memory map of the final hardware where it is supposed to be running. So your target hardware may have a flash somewhere or a RAM somewhere in some memory. They are mapped to that particular addresses. So you have to make sure that our data or stack reside in this memories. Okay, or OS may be there. So those things we have to mention it in the link file and then generate an executable. So this is what is done in the using the different tools and the different software provided. Okay. So what are the development tools? So this is a development studio. It is a professional software development solution for Linux-based embedded systems. It covers all the stages in development, from boot code and kernel porting to application debug and profiling. What is the profiling? You would like to know which part of the module is taking more time. Okay, you may be interested to know that in your application. And then if it is suppose very critical and you feel that it is taking more time, maybe you may decide to optimize this much better than what you have done earlier with the tool, compiler tool. And then still if you feel that it is not meeting your requirement, maybe we have to write a assembly of that exact same, part of that, or maybe a sub portion of that in assembly, and then see how it performs. So this kind of measuring the time taken by a particular routine is not possible with the profiling tool. Okay, it includes this tool development studio includes the IDE. Okay, it's integrated development environment. Eclipse is a a language or a platform which is useful to develop a GUI. Okay, so this IDE is Eclipse based. So it is very easy to interface with the. You can add on, we can put even the simulator that we are using is an Eclipse based one. Okay, oh, no, sorry, that is a different thing I'm talking about. So let us not bother about those tools. This particular development studio is Eclipse based. So compilation tools, they are fully featured graphical debugger. Okay, I told you what is a debugger means. Simulation model. Maybe if your target platform is not there, maybe you can use a simulation model to run that in the software itself, in the PC. So without having a target hardware, the whole thing can be simulated in the PC along with the software running on them. So there are so many examples of Linux code, and then so this basically they are also used by the semiconductor companies who build the SoC based on the ARM. So when the semiconductor companies they build a SoC with ARM, they finally they will be selling the SoC along with their software, okay, to other vendors who will be using their chip with their hardware. So while the semiconductor company is building the SoC, and then they need to check test their minimum porting of OS. Okay, it may be an in-house OS, or it could be a Linux or any other third-party OS or freeware, and then they will be adding their own library. So for them to do the basic software that needs to be run on the ARM, as well as the SoC. SoC in the sense it will have other peripherals, menus and cache. So they may have to optimize those things and then develop a OS. So running on it. So they more than the application developer, even the semiconductor companies who are building SoCs based on ARM will be using these tools. What are the debugging tools? DSScreen is one. So ARM debug and trace hardware unit. What is the trace hardware unit? It's actually ARM processor is there. Okay, it will have its own trace buffer. It's called some trace buffer. I'll take it to me. So while the program is running, it will be keeping some information in the trace buffer, which can be downloaded to a PC. So what is the need for it? Suppose the software is running in the hardware and you want to know at a particular time when there is a crash or the software is failing and then exception is raised. You want to know what has happened or which has led to that particular crash. So the trace module keeps the behavior of different the values of registers or memory stack, what all the things change, those things are captured there, so which can be downloaded, and then the detailed analysis can be done on that output to verify or identify the problem. It could be a memory problem corruption, or it could be a software bug, or a pointer may be corrupted. All that can be debugged using a trace hardware. Okay, so it enables to connect a software debugger to ARM processor based target using a hardware interface such as a JTAG or a serial wire debug. Okay, this is the JTAG is the Joint Test Action Group, the expansion is. So this is a generic hardware as well as software definition to verify and then get the values of particular processor or a chip. So it can actually go into that and then get those bit patterns out. Okay, so basically you can even configure the particular values in the registers or peripherals, or even we can make the ARM processor to run a few instructions by feeding in some data into it. So the JTAG is an interface, hardware interface, which can be understood by the debugger. Okay, and while building the chip also that JTAG support should be built into it. Okay, so then only a JTAG cable can be connected, and then we can talk to the hardware through this JTAG hardware interface. The debugger understands how to make use of it, and the hardware has a support for that. So this much of overview is enough. Maybe we can read more about JTAG later. It also enables collection of trace from a device. Trace means a different capture of data from for non-intrusive debug and code optimization. Okay, so it is a comprehensive solution for development and debugging a complex SOC. That's the summary. So trace is an essential tool for resolving complex timing related issues. As I told you, whether any particular module is taking more time, maybe that also can be resolved, or any particular interrupt is coming, and then there is maybe some event is happening at a particular time when the system is crashing. So this kind of very specific events can also be traced and then analyzed to find out the cause for a problem. It enables post analysis of a software execution without the need for any modification to the software or hardware component. So actually in most of the real time scenarios, we do not want to tweak the code in the sense add more elements or modify the product final software which is going to be running in the hardware and then debug it. We want to debug the exact hardware which is going to be in the system. So if that is to be done, then we need to have a hardware support which is a trace buffer and trace hardware unit, so that we don't have to change the software image or add more modules to the software to get some information about what is happening inside. So the hardware non-intuitively gets you information about what has happened while the software is running in the hardware, so that we can debug it and then analyze the issue and fix it during the development phase. So compiler toolchain, ARM compiler toolchain can be used to build programs from any language, high-level language or assembly, and then ARM and some C++ compiler. Normally, the tools are called ARM-CC. ARM-CC, if you call it as a vectorized, then Neon vectorizing compiler is invoked. This is SAMD that I talked about BFP. It supports this feature so that vector instructions can be integrated, okay, along with your software. Of course, if you are using BFP, then we need to have invoke this. Otherwise, the normal ARM-CC compiler may not understand your vectorized, BFP related instructions. And then ARM and some assembler is ARM ASM and linker is ARM link. And if you want to build a library, then you get ARM archiver. That's what AR means. Then what is this? So normally the output format is called AI, embedded linking end. Okay. This format may not be compatible to a particular hardware. Okay. So from else to some different binary format, okay, is more than the hardware. We want to use some tools, maybe flash tools or a loader tool, to load the binary file that has been generated into the hardware. Okay, so you may have to, if a flash memory is there, we may have to write the executable. The code has to be flashed into the flash which is there in the hardware. So that may need the format something different from the what this linker generates or executable comes out of the ARM tool. So there is the ARM tool which converts that L format to a compatible binary format, which could be understood by the flashing device, flasher device, or maybe a loader to load into the hardware. Okay, the image has to be finally put into that. So what the image may have, it may say that in this particular address, a particular binary, that is a code. Okay, that all the assembly instructions converted into encoded into a 32-bit format. No, it will be giving the address and then what's the content. So address content. So it may be expressed in some particular format, so that wherever that is mapping to this in the flash device, in that location it has to be put. So it is a time consuming job of flashing it. So there are different tools available which can understand only particular format. Then we can have this tool to convert that from the output coming out of the tool chain, output tool chain, that is ARM tool chain, and then put it into the hardware. So that is the job of this. Convert other formats suitable to RAM tools. Okay, support libraries, as I mentioned, some of the functions or VSP related things, or even calling a main routine. Before that, there are so many things. You remember, recall, I mentioned that stack pointer for all the modes have to be initialized. So that could be a library, and we can feed that information also, or it could be done by OS. So OS also may be integrated. So those things also have to be finally integrated with your application, and then finally executable is got, and that will be put into the ROM or a flash using these tools. Okay, there are some application binary interfaces. Okay, that is called API. Okay, what is it? So API for ARM architecture is a collection of standard, some open and some specific to ARM architecture. It regulates the interoperation of binary files and development tools to in a spectrum of ARM architecture based execution environment. So there are some standards. I will explain you with some examples so that you understand. So those things have to be adhere. The development tools need to adhere to these ABI, which has been defined by ARM, so that suppose different companies are developing tools for the ARM processor. So when you have an OBJ file from this and then some other OBJ file from here, and then if you want to link, maybe you want to even libraries are generated by some tools, and then you want to integrate it with the some other output tools coming from output files coming from other tools. So there should be some standard defined so that there is some uniformity, and then they can interoperate. Otherwise, there will be too much of confusion in terms of who is developing the library, with which tool and which version of the tool. So there are too much of unambiguity can come in when the output files are only integrated with the rest of the files that we have. So there should be some standard to be followed. So that is defined by these APIs, and then all the tool vendors will be following that. Now it would be useful for from bare metal to major operating systems such as ARM Linux. So what is bare metal? Bare metal means that just the processor is there and memory is there, all the hardware is there. Okay, there is no OS running there. So if you want to run your code without any OS, then we have to take care of locating and putting everything, and then if you are creating multiple tasks, how do you move from one to the other? All this needs to be done. So that's the bare metal method. Otherwise, you may have a preloaded OS, and then you have to add only your application side. So ABA for ARM architecture includes, okay, this is standard ARM architecture procedure for standard and executable usable format. And what is for this is the executable file output. Okay, how a particular sections are defined, how static data is defined, how global variables are defined, how they are located. So code, this kind of, there is a standard format for that. Okay, and ARM has defined something specific to its own register specific details. Okay, so ELF format is generic to any process. It is not under assuming any particular architecture, because ELF format is common for any processor architecture. So ARM has to map to the ELF format. So it may say that, okay, my register R0 is mapped to some other register which is defined by ELF. My R1 is mapped to this. So this kind of a register format specific to ARM is defined in this document, ARM ELF. ARM doc is how to understand the debug information in the executable, so that when you are using a PC for debugging your software, you are interested in looking at a particular variable value, where actually a variable value may be a integer a, but it may be finally converted to some some address in a data area. So how do you link this address with the label, the a variable a? So this kind of information is captured here in a debugger, block format. So the base platform ABI for C++ ABI, exception handling ABI, runtime ABI, there are so many available. So it may take 10 or 15 hours to even go into each of these details to talk about it. But the intent of this particular lecture is to give you an overview, and when you go into those tools and documentation, you will be able to appreciate what is given there. So now our focus will be for this class is going to be to understand how do we link C source file and an assembly file, and how do we talk to each other. Okay, how there are some parameters, some C, if suppose you want to pass it, how it is done in the. So by generating a C file, converting a C file into a .s file or assembly file, and then looking at the output, we'll be able to find out how a particular C calling function, a function call is converted into assembly. So it will give you a overview of what happens there. Okay, that's my intent in this lecture. So ARM, so what is APS? ARM architecture procedure called standard. Okay, ARM architecture procedure called standard defines how subroutines can be separately written and separately compiled and separately assembled to work together. So there should be common understanding between them. Okay, let me explain that. Suppose you have a.c file, okay, and then you have a b.c file. Okay, here a defined function f1, and then it is passing an integer I. Okay, so this readable, and then you are in here it is called. Okay, you are using this function and passing some value 5. Now, while compiling this, the compiler has to generate some a.obj. Okay, and while compiling this, it should have generated some file called b.obj. Now, these two, when they are linked, this assembly listing and this assembly listing will be combined together, and then it will, it may be branch to, it will call branch link maybe to call this routine. Now, while generating the assembly file, okay, the obj file is nothing but some ASM file, right? Assembly instructions. It should know where to keep this, where to pass on this value file, okay, so that this function, when it is looking at some registers, it will be able to take that value. So while generating this obj, it doesn't know what is being followed, convention followed by this. While calling this function, what the compiler does. Okay, so there should be some understanding how the function needs to be, parameter needs to be passed, so that the compiler which is compiling this and generating an ISM file, it will know how to make use of the variable or parameter coming from the other routine. It may know this a.c and b.c for that matter may not be written by the same person. It could be a same company. It would be coming as a library. Okay, the whole thing. Done by somebody else. So there should be some common understanding, so that the calling function, how is it passing the parameter, follow some guidelines, so that the called function can read it from some known location, so that it can proceed with its own function or processing that particular parameter and then performing some job. So while generating the assembly file, the compiler should have some understanding. Okay, this is where I expect the parameter to be in. Similarly, when a compiler, same compiler or different compiler is generating this output file, should know how I am going to pass this parameter, so that this routine, which is compiled by somebody else, okay, can understand this. So there should be a common understanding between them. Okay, caller and a calling. So calling routine and a called routine, that's different. This is a contract between them. Obligation on the caller. Caller is what? Who is calling this function? Okay. This is the called function. This is the caller. This is the caller who is using the function, and this is the called function. Okay. So there should be some contract between these two. So obligation on the caller to create a program state in which the called routine may start to execute. Obligation on the called routine to preserve the program state of the caller across the call. So there may be, see, finally this function and this, okay, they are all using some set of registers. They are all running in the same processor, and they are all using some registers in the processor. So this is also going to use some registers. This is also was using some registers, and then it is calling the function, and then later on it may use some registers. Now here it is inside the function, it is going to use some registers. Now At the end of the game, what happened? The control goes there and then comes back here and then executes. So as far as the set of routines are concerned, it is like a BL executor. Okay, it goes there and executes some set of things and then comes back to the next instruction and then continues. So there were some register uses before and there were some register uses inside the processor. So and then of course the stack also. So there should be some way the whole thing works without any problem. Just because we called a function, if our routine gets disturbed, then there is something wrong with the way the called routine is implemented. So the contract is broken. So the APS, the ARM architecture, okay, this platform thing, how do we calling standard procedure calling standard is how is it making sure that there is no confusion because of a subroutine call. The rights of the called routine to alter the program state of the caller. Okay, called routine can also change something so the caller gets to know about it. Why? Because it may be returning some value to you. So the caller should get some value from the call routine. Otherwise, why are we calling this function? So there should be some understanding where I will be passing this to you, and then where I will be passing the parameter to you. There should be some understanding between these two. Okay, that's what it actually the whole thing is about. So it supports some state and then on state equally, and then support interworking between some and on state. Support efficient execution of high performance implementation. High performance on the ARM architecture. High performance in the sense it doesn't waste cycles. Okay, it does it in a very efficient way. The generated code clearly distinguish between mandatory requirements and implementation decisions. So we cannot actually, we have to give some freedom to the tool vendor, okay, who is generating OBS. If everything is defined by a standard, then one tool, there may be so many C compilers for the ARM processor. One may be performing better than the other. So how is it doing? Is because of the ingenuity or intelligence, the innovation that each tool vendor incorporates in their implementation. So there should be some freedom for the tool vendor to make use of the architecture, okay, and then a particular language construct. See, they have to play around with the architect. Suppose they are developing a processor, as a tool for compiler for ARM. They have to make use of the ARM architecture features. And then if they are writing a compiler for a C language, the C language syntax and the semantics are also to be adhered to. Using these two, they have to generate an output, an assembly listing, which is efficient. One tool, this is the tool from one company, another tool C2. The both may be getting the same C and then it is doing it for the same ARM assembly, but what the output may be different. That is because of their innovation. So that kind of implementation freedom is given to the tool vendors so that they can optimize it based on what are the switches. Then they will give some different optimization switches to tweak the output. So this is all done by that. So the APCS, the standard gives you some guidelines, but within the limitation, they will be able to innovate. Minimize the binary incompatibility with the minimize the incompatibility. So ARM from PCS, it was earlier ARM from PCS was the older version. Now the new version is the APCS. Okay. Now what are their variants? The standard specifies the base for a family of procedure call generated by choice that reflect alternative priority. What do I mean by that? Code size. It could be that I want to generate a output which is occupying a less footprint. That means the code size is the minimum. I don't bother about the time taken. Okay. Performance is the cycle time. I am not so much concerned about how much code size it takes, but I want it to be faster. So we can give speed or code size. Okay, speed is one and size is one. So based on the target platform, maybe if the memory area is limited, then we may say that I want to optimize the size. But I may be ready to give you more memory, but I cannot sacrifice on the time taken for the execution. Then these options can be given. So the tool should be able to generate the output based on different priorities. Okay. It could be functionalities, ease of debugging. I would like to get the output generated such a way that the debugging is easier. Runtime checking is easier, maybe. Support for shared library. So I don't want no executable to be having all the libraries to be interface, connected to the or the built with the library. So shared library may be there, which will be used by multiple applications. Okay, and it is dynamically linking the library. So you only what is required may be linked with the executable. So final executable, whatever is got, will be smaller, and then shared library will be separate. So these kind of different priorities will be there, requirements will be there, and the tools should obey these things and generate an output file based on that. Okay. So let us see how AAPS is defined. Okay. So as just to refresh your mind, what AAPS tries to do, it is trying to C files are there, and then okay, some ASM files are there, or the registers are there. So how do we between two C files? How do we know how parameters are passed, how return values are got? Those understanding is what is one. And then another thing is the language will have some data types, right? Standard data types. Now, how these data types are mapped to the processor hardware. So ARM is having a 32-bit register. Now, the C language defines some data type. How is it mapped to the particular architecture? So that is also defined in this standard. Okay. So this is where if suppose unsigned byte is there, it will occupy one byte and then it will be byte aligned. That's what I mean by byte aligned in a memory. Okay, a byte value can be on any address. So 1000. Okay, and back into our famous address. So if you declare a variable character, okay, it's an unsigned byte. It will occupy one byte value. It could be on even odd value, odd address 1001, 1002, or 1003. It could be placed anywhere because it's a byte array. Okay, signed byte also can be like this. Unsigned half byte, it can be on 2 byte boundary. Okay, maybe we can have a short variable. Okay, which is 16-bit value. Then we can store it in half byte boundaries. It could be a signed or unsigned. So normally we can write it as unsigned in the C language or signed in. Okay, so based on what we choose, it will be interpreted inside. And as I explained you long time back, the instruction generated will look at the overflow flag or a carry flag based on what type of the variable is being looked into. Okay, this variable may be finally mapped into some register and it will be performing some arithmetic. Then if we have to check whether less than or equal to or greater than or whatever, it has to either check whether overflow flag or carry flag based on whether signed of arithmetic was done or unsigned arithmetic was done will be interpreted internally by the generated code. So bird can be on 4 byte boundaries and unsigned W will be of 8. Fine. So floating point, they have one new thing which I have not explained earlier is the half precision. So actually floating point, that sign bit is there, okay, and then original 32-bit all of us we have seen in detail. So now I am explaining you what is the half precision value. So this is 1 bit, okay, these are 5 bits and then this 10 bits, okay. So the exponent portion is here, okay, and then the Mantrasa Mantrasa portion is here. That will 1 dot, if you remember, minus 1 whole power s, right? 1 dot s, okay. This fractional part is here. The exponential part is here, okay. Only 5 bits. So this is actually if wherever there is a memory constraint, a single precision arithmetic will be done in 32-bit, okay, inside the floating point processor, and then it will be saved in the small 16-bit value. That's called this half precision value wherever there is a memory constraint. So that was not covered earlier, so I thought I will just talk about it when we discuss this here. And then single precision, you know, 4 bit and 4 byte and 8 byte, and then if it is a vector, it is only 64 bit vector or 128 bit vector, and then the data pointer or a code pointer. What is the data pointer or code pointer? Is whether you are accessing int star, okay? You must declare that int star p int p, okay? If this variable is there, how much space does it, where is it stored? It is a 32-bit value, okay? Why 32-bit is enough for a pointer? Because our addressing range is only 32-bit, right? It can vary from 200 to 32-bit or less, right? So 2 power 32. So the whole address range is only this much. Either code or data has to reside in this limit. So 4 bytes are enough for keeping any of the pointers. So pointer arithmetic should be unsigned. Why should it be unsigned? Because anything that you do is actually the value that we are using for the pointer is all from 000 to FF. Everything is an unsigned value. Okay, we are using all the 32-bit bit pattern to indicate address different locations in the memory. So they have to be unsigned. So any arithmetic that we do on pointer needs to be unsigned. It can't be signed. Okay. But when you want to actually go from this address to this, you will be subtracting it and then going here. Okay, but that arithmetic will be unsigned arithmetic. Okay, so we won't be interpreting the value address pointer value as a signed value. That's what it means. Okay, we won't interpret it as a MSB is 1, so it's a negative value. No, it is a positive value always. Okay. So bit 0 of a code pointer indicates the target instruction set type. If you recall, the bit 0, okay, if it is set, it is pointing to thumb instruction. So if it is pointing to instruction, it will be a code pointer, right? So if thumb instruction has to be executed, the code pointer has to be having the bit 0 as 1. Then only internally the processor interprets it as a thumb instruction and then fetches only 16-bit values into the pipeline. So the compiler or assembler takes care of putting the 1 based on your dot time or port 16 or port 32 if you mention, then it generates 16-bit values, and then it also generates if any address coming here, it will make that bit 0 as 1, so that the processor knows that it is going to fetch some instructions. So there are 4 registers. Okay, this you know that. So program counter and then link register which is the exact return address, and then a stack pointer. Okay, which points to the stack. So LR is holding the return address of the subroutine call. Stack is the contiguous area of memory that is used for storage. You know that as we issue for local variable as well as additional argument. Why additional arguments? Some arguments are coming in register. Okay, I will explain that as we do. So when you are calling a function, okay, the actually language doesn't restrict on how many parameters you can put. Maybe there are some limits are there. Maybe the tools may limit it because you can't say thousands of parameters, but still, it is not just a few, 1 or 2 parameters. You can pass even 11, 20, 30 parameters, 20 parameters also you can pass. So in that case, when we pass more parameters, the architecture allows some optimization. In some few registers, it is allocating to pass a parameter. Okay, I will explain that in a minute. The parameters can be passed in the register rather than in the stack. Okay, though when you studied about languages, you might have heard that the parameters are coming in the stack. That is not always true. All the parameters are not, residing in the stack. Few of them will be in the register itself. And then if the parameters exceed the limit, then they are passed on to the stack. Why we try to pass it onto the register? Because it is easier in terms of reading it and then updating them, using them inside the function. So it is easy for the calling routine as well as the called routine. Why I say easy means we don't have to do a memory access. If you have to store it in the stack, it has to be done with the LDM or SDM, which is involves some memory. And similarly, the call function needs to read the parameter. It has to use the SDM or LDM to get it into the registers to process it. So passing the parameters through registers saves a lot of time in terms of execution. So to achieve that, but we cannot have too many parameters to be passed because there are some limited registers available in the process. So maximum four in this case, four parameters are passed in the registers, and then more than that it is actually assumed to be in the stack. So this knowledge as a programmer, if you are aware, then maybe you design your system or a software such that you don't pass more than four parameters in a function. You will partition the functionality into functions such a way that it doesn't need more than four parameters. In that case, you will be optimizing it in terms of execution. So this awareness is very required, essential for an application developer, because they can optimize their routine properly. If they write it, then the generated code will be more optimal. So better code will be generated. So stack implementation is always, though as I explained you earlier, there is a different ways of stack implementation. Means it can be passing at full or empty, or it can go it is lower at an higher address. That suppose, okay, let me call it yeah, this is the higher address. So in this case, it may grow towards top, or it can go towards bottom, or it can be pointing to a full location or empty location. That means first push the value and then increment it, or increment it, or first increment it and then push it to the stack. So there are four possibilities in this, I explained you. But when we are having a multiple functions compiled by different tools, and then they are all linked together, we can't have one person following a full descending, other person full ascending. It will be a confusion, or not even a confusion, it will not work at all. So because the stack, what it is being passed into this, what it assumes it to be, the stack is implemented, which is being followed, that assumption should be common across all the tools. Otherwise, it won't be able to work together, work with each other. So full descending is what is assumed everywhere. Okay, and with the current extent of the stack size in the SC. So stack pointer also should be assumed in all the places to be R13. Stack may be in general have both base and limit. Okay, normally a stack has a how much of space it can occupy maximum, and then where it starts, stack is starting. So most applications may not be able to estimate the limit accurately, because how much of stack usage depends on what is the calling depth. Okay, suppose a function is calling this on another function, this function is calling another function. Okay, and then how many parameters are passed, how many local variables are defined, all that decides how much of stack depth it goes. Okay, so the limit of stack is very difficult to guess, but it has to be estimated, because you can't say that I don't know how much stack I want. Then means you cannot say how much of memory is needed in the target system, because stack needs to be in a RAM somewhere. So we have to have a profiling. Let's say profiling is required, and then understand how much stack it goes. Based on that, we can allocate the stack for a particular application or a particular task. So that's a very important point, because you might have heard any software crashing is mostly because of stack overflow. Okay, so you have to be very clear about how much of stack is used and how to use them, how to optimize it in terms of writing the code, as well as in terms of executing it or calling. Needs to you have to keep in mind that how much of stack will be consumed by a particular function call. So arbitrarily you cannot define local variables. Okay, huge arrays of local variable will be a cost for one stack. So in that case, you should declare it as a global variable, maybe a huge arrays, or do a dynamic allocation. There are so many ways you can optimize the make sure that the stack is not consumed more. Stack may have a fixed size or maybe dynamically extendable. Some, if OS support is there, maybe we can dynamically extend it. So that will be adjusting the stack limit dynamically. That then OS needs to come into play. Very good. So now let us see few more registers. So when a function is called from one to the other, the IR12 is used as an intra-procedure call. What I mean by that is function, okay, F1 is calling F12, okay, that is calling F13. So there should be, I told you, some understanding between the functions. what are the registers this can use, what are the registers they can, they are not supposed to use the call the function, those are all defined. So the R12 is a from register, is a stack register. It can be used by anybody, and it is used across the function call. Okay, maybe to pass some values between them. Okay, so that's a kind of a understanding. In the intra procedure stack register, and then these are all variable registers. What I mean by variable register is these registers, okay, can be used by the call routine provided they save them and then use it. Okay, so we don't, that is one thing. Whenever you are using this register, let us make sure that you save them so that we don't disturb the caller status. Okay, I will show you an example, then you will understand it better. Okay, so it can be used for creating local variables or for the function to use process some parameters are passed, but they need to use some more registers to do the function. So you are calling a function to do perform some job, so it needs some registers to do that. So they can use these registers for its operation. But this R9 is sometimes it's called frame pointer, and then it is used as a frame pointer, or it is very application specific. Okay, we will not go into the details. So R12 is the intermediate values between subroutine call, and R9 is the platform specific, maybe static base points to base address of static data segments, or suppose initialize value or static variable is there in your routine, they will be used. Okay. Okay. So if you don't follow so much, it's not a problem. We will see the example, then it will become clear to you. So one thing you remember, these are all variable registers that are used by the call routine. Okay, that's what I'm saying. And now these are all the argument registers. Okay, R3 to R0 to R3. That means a function call with multiple parameters. They are first argument, second argument. They are all passed into various registers. As I told you, 4 arguments can be there maximum. If you need to pass more parameters, that needs to be passed into stack. Now let me explain you what I mean by that. Okay, a function, suppose if n is calling, fn is called from f1. Okay, f1 is a function, and then it is calling fn inside that. Okay, this is supposed to be a flower bracket. Okay, now before calling this function fn, the stack at f1 will be like this. Okay, stack is going downwards. Now SP is pointing here before, just before calling the function. Okay, now this is what is used for parameter, extra parameter. Okay, the previous slides I told you guys, extra parameters are passed apart from these 4 parameters which are in passed through registers. If the caller wants to pass more parameters because the function wanted more parameters to be passed, okay, it is not restricted with the 4. In that case, that can be pushed into the stack by the caller. Okay, caller routine. Okay, and then now what happens? The same stack. Okay, up to this is what is passed by the caller. Okay, now it has come into the function. It's inside the function. Now function inside that some assembly registers are there. Inside what it does, it first saves LR register, because why? If it doesn't save, and then if this function is calling another routine, suppose F2, it will be converted into finally in assembly as a BL, right? Branch with the link register. Then it will overwrite the R14 register while calling this routine. So then the previous R14 is lost. Okay, when this function was calling, it was actually BL to that function. That time R14 was saved. R14 was having the return address where it is supposed to come. But once it is not saved at the entry of the function, okay, if this function is calling another function, then it may be overwritten, because the BL instruction default pushes pushes the return address into the R14 register. So that needs to be saved first. Okay, these are all called prologue and epilogue and prologue and epilogue. Okay, so before getting into the function, these are the jobs done by the. These are all generated by the compiler. So link register is saved, and then what we have is this R9. Okay, the frame pointer. That is what is used as a R9 is used. I will show you an example to access the stack. Okay, and then any registers that the called routine wants to use, they are pushed into the stack so that they don't disturb the register values which was there before the function was called. So that will be saved, and then local variables are kept. Afterwards, maybe local variables. If suppose if you are declared local variables, they will also be in stack. So suppose you are declared inside the function, you are declared, in the function you are declared in, I10. Okay, this 10 32 byte 4 byte values are actually residing in the stack. So what happens is, what is the what after this routine is returned, suppose you assume that F2 is not called. So after the function is done, it comes back to this location. That time what it does, it restores the stack back to the location how it was prior to the entry. That means what, this function assumes that the stack, nothing was happened to the stack, so it will go on with its own value. So whatever it had R13, it comes back to the location. So when the function is called, it uses the stack and then gives it back while coming back. So this is what is done on every function call. I hope this is clear to you. So R0 to R3 are used for passing argument, and then you see this, these two are special ones. While returning, the return value can be put in R1 or R0. So it does the two jobs. It brings in the value into the function, and then it takes back some return value while going back. Okay. So let me tell you what it. Maybe the example we will see. Okay. So register R4 and R8, R12 are used for local variables. Okay. So they can be using it, the function called the function. You could use it for local variables. Apart from that, if they want to have more local variables, then they need to use the stack. Because if you are having an array of 10, 15 values, they can be kept in the register. But if you have smaller one or two variables, I or j, which you normally use it for loop, those variables are normally kept in the register so that they will be faster in the execution of for loop. Of this, the variable v1 and v4 can be used for sum. Okay, sum state, you know that there are only R0 to R7 are available in sum state. So these 8 registers are only used for the sum state, in the sum state. So a subroutine must preserve the contents of the register. So that's what I'm saying. When you say that you can use it as a local variable, they have to preserve it. Okay. So call routine assumes that these variables are not going to be, these registers are not going to be changed by the call routine. So if the call routine wants to use it for local variable, they have to save those registers into the stack and then restore them back before coming over the function. Then only these values will not be modified. Just it won't be changed by calling a subroutine. So this has to be followed. That's the contract between the call routine and the caller routine. So if they are using any of these registers, they have to make sure that they are restored, they are saved into the stack, and then the call routine can use them, and then they are restored back before returning. Then only the caller will get the same, effect, whatever was the status, except for these 4 registers. The caller doesn't assume that other registers are modified by the call. In a summary. Understand this? Okay. You know how larger data types are managed. Double words are passed between pair of registers. It is similar to some LDM multiple store from memory. So both registers are used for that. So okay, based on the NDNS, what will be residing in R0 and R1. This depends on the NDNS of the machine, but it is similar to what LDM. LDM also is it will change based on, see, when you have a double word, this 32 bit is there and this 32 bit higher. How it is organized in the memory in after some memory when you are LDM you do depends on which is in the first location and lower address and higher. So based on that it will be decided. And then 128-bit containerized vector, that is if you are having vector in 4 consecutive registers will be used, because it's 128-bit is 4 into 3. Content of the registers are contiguous registers, consecutive registers, okay, R0 to R4. That's why 4 registers are there, so you can pass maybe a 128-bit vector into a function. So returning the result, the following data types R0 and R1 are used for returning. Off position values are converted to the single position because register is 32 bit. So this is where the return values are. So it's going to be converted into single position and passed back. Fundamental data types are 4 bytes. So integers they can be as it is saved. Whereas if it is smaller than 4 bytes, it will be 0 extended or sign extended to a word based on whether you are passing an integer signed value or unsigned value. Similarly, word size fundamental type will not have key, we will have keying at all, will not have any key. So even float value, okay, please remember float value also can reside in a register, okay, R0. So because effectively float is of 32-bit value, so it can reside in a register, and a function which uses the floating point values can return a value back to the calling routine in a register R0 or R1, okay, stored into the register. Like double precision value or 64 will be using both the registers, and 128 will be using 128 bit will be using all 4 registers. And then its composite type not larger than 4 bytes is written in R0. Okay. Now composite type means it could be a structure or any 2 kinds of data types, but they are not exceeding 4 bytes. It will be put into R0, but they need to be interpreted accordingly by the language, the compiler, or the call routine, as well as there should be some understanding between the caller and calling. Okay, if it is larger than 4 bytes, it may be stored in a memory. So which address it has to be stored in the memory. Suppose the function wants to return a huge value, okay, in the sense it wants to return 10 bytes of value or structure, which is occupying 10 bytes. It can't be passed with the 10 bytes. Maybe you can do, so let me say 40 bytes. Okay, so maximum we can have 4 registers that can hold the return value, right? So each of the 4 bytes, so 16 bytes, maybe we can try to pass it on to the 4 registers, right? But if it is more than that, a structure if you want to return, then what happens? A pointer to a structure will be passed, or okay, there are some restrictions, and then if you want to maybe an array, and then we are saying that that much of value needs to be passed back, then what we can do is the caller will pass on a pointer where that has to be saved. Maybe it's a data area, and then it would have allocated that much space because it knows how much of data is expected from the call routine. So it will be saved by the caller and then it will be returned back. So these are all very specific implementations. So I don't want to go into the details of them. So the caller decides the location of the call, and then call stores the result in the location and returning back to the caller. Okay. The memory to be used for the result may also be modified at the point. So there is possibility that even that could be modified by during the function call. Okay. So let us not go too much detail into this. Now example C program. Okay. So This is the C program, okay, which is my app taking two parameters and then it just adds these two and then puts in the result and then returns the result. Now, if suppose if I want to call this from my assembly routine, okay, so this would have been a C file, so it is compiled and then it generates a .s file. Just take an output file to show you what is the output generated file. So I use the mental graphics tool. Okay. Here, what is done? Okay. Sorry, one second. This is not output file. This is the original source file, assembly file, which is calling this routine. Okay. I'm calling this routine from this. I will show you the output of this file later in the slide. So this is the written. I have written an assembly file to call this routine. So I have declared two variables using the simulator that we use for this course. So these two variables are initialized to these values. They are already loaded. LDR is loads the value where the num is stored in the data area where it is located, and R1 has this value, the address where this particular variable is defined, num1 and num2. So they are accessed and then put into R0. Now R0 has this value, R1 has this value. Why am I copying into R0 and R1? Because I know that C convention says that R0, R1, R2, R3 are the parameters to be passed. And then first parameter is expected to be R0. This is supposed to be in R1. Because this is going to be compiled by the another tool, they need to understand where these variable arguments are coming in to which registers. So that's why I am using the AA the ROM architecture procedure call standard, which says that you pass the first two parameters or three parameters in these registers. First parameter here, second here, third here, fourth here. So R0 and R1 I am talking the num1 and num2 values, and then I am calling this my add. Now BL, how do I call? The branch with the link register my add. Now, when I am running this code, I should have compiled this and its OBJ file also should have been linked with this file, and then the executable should have been put into the simulator. In that case, this routine is also there somewhere in the memory and it will be resolved by the linker so that it will know which address it is residing. So it will call the routine with this instruction. Now, when this is called, the R14, the link register will be having the address where it has to come back. It has to come back here. Okay. Now, assume that something is done by this function and then it comes back. When it comes back, it is supposed to store the value in the answer. Okay. That's what I'm expecting. So I will get a variable called answer. So that address is put in R4, and then I am picking that value returned from R0 because the result is supposed to be passed by the routine or the routine in R0. So I expect it to be in R0, so I store it in the on the second. Hello, hello. Hello, hello.